Welcome back, everyone. This is part B of concept video for 11.4 comparison test. So earlier in the first part of the video, part A of the video, we showed an example for comparison test. Uh, so we just did the regular comparison test. In this part of the video, you're going to see another comparison test known as limit comparison test. In the regular comparison test, we have the condition that an less than or equal to bn or an more than or equal to bn in the comparison test. So if you see, go back here and see these results here. So we have an less than or equal to bn or an more than or equal to bn condition is there. Um, we need verify that it holds for all n more than or equal to n. So even though an is less than or equal to bn or an more than or equal to bn is need to be established, if it happens eventually, if it happens ultimately, then it's okay to have that condition. Still, the result can be applied. Comparison test can be applied. Where n is some fixed number because the convergence of the series is not affected by finite number of terms. See, if you say sigma varying from, suppose you say sigma n varying from, let's say 100 through infinity, an is convergent by some test, then automatically means that sigma 1 through infinity an is also convergent. So what is the difference between n starting from 100 to n starting from 1? So the difference is only 99 terms. It starts from the first term, the second one. If you start from n equal to 100, it starts from 100th term. So the difference is only a finite number of terms. As long as it's only finite number of terms, the convergence is not affected because um, the convergence is same for both. If the first one diverges, the second one should diverge. If the first one converges, the second one should converge. That's the point. So the convergence of the series is not affected by finite number of terms. The terms of the series being tested must be smaller than those of the convergent series or larger than those of the divergent series. If the terms are larger than the terms of convergent series or smaller than those of the divergent series, then the comparison test does not apply. What it means is here, um, you have convergence for sigma bn. If you have convergence for sigma bn, but instead of establishing a less than or equal to bn, but if you establish an more than or equal to bn, the comparison test does not apply. So if you're saying convergence, you have to only go with the first condition. Then if you're going with divergence, you have to establish both um, both results of one being sigma bn divergent, and also you have to establish nth term of an more than or equal to nth term of bn, sigma bn. So these are, you have to be careful when doing these problems when you do direct comparison test. Let's try limit comparison test. What does it say? Suppose sigma an and sigma bn are series with positive terms. If limit is n approaching infinity, an over bn equal to c, where c is a finite positive number, equal to c, where c is a finite positive number, and c is more than 0, then either both series converge or both diverge. They converge or diverge together. Let's try this example. Number 3. Test the series sigma n varying from 1 through infinity 1 over 2 to the power n minus 1 for convergence or divergence. So as I always say, this without the sigma, it has to be equal to a sub n. So step number 1, We'll apply limit comparison test. So you should always state which test you are applying. And then step 2, you have to pick the series that you're comparing to. So choose sigma Bn. It should be a well-known series. It is sigma n varying from 1 through infinity. When you choose, you look at the given series. The numerator is a constant. You choose that constant. The denominator is 2 to the power n minus 1. You choose the leading term, that is 2 to the power n, the highest exponent in the denominator, which is 2 to the power n. So is this a well-known series? Yes, of course, it is a well-known series. So it is, you can write this as 1 over 2, 1 over half, 1 half to the power n minus 1. So this is of the form sigma A times r to the power n minus 1, which is clearly a geometric series with A starting term 1 half and common ratio equal to 1 half as well. And the absolute value of the common ratio is less than 1. Therefore, the series is convergent. So always, that's why we choose a well-known series, either the P series or a geometric series. And now we are going to apply the test. So now you do an over bn. We have to show that that limit as n approaching infinity, the value that you get for this limit should be finite and positive. So it is an over bn. An is the given series, the nth term of the given series. Bn is the one that we have chosen, which is 1 over 2 to the power n, which is a geometric series. And we simplify this, it is 2 to the power n, 2 to the power n minus 1. Now we apply the limit as n approaching infinity. So if I apply the limit right away, it is infinity over infinity type, so which doesn't help. So what we are going to do, the usual trick, divide the numerator and the denominator by the highest exponent of the denominator. So we divide the numerator and the denominator by 2 to the power n. So this will be limit as n approaching infinity, 2 to the power n over 2 to the power n, that is 1. Then for the denominator, you divide each term by that 2 to the power n, and it's 1 over 2 to the power n. So this part is going to be 1. This part is going to be 0. 1 over 2, 2 to the power a large number, infinity. So 1 over a large number, that will become 0. So you get limit n approaching infinity, an over bn equal to 1. 1 divided by 1 minus 0, which is equal to 1. So this is C, which is finite and positive. So what is your conclusion? By limit comparison test, LCT, limit comparison test, by limit comparison test, the given series sigma an, which is sigma n varying from 1 through infinity, 1 over 2 to the power n minus 1, converges. Converges, it is convergent or divergent as per sigma bn. Sigma b sub n, we mentioned before, it is convergent, and therefore sigma an also converges. Let's try one more example. Determine whether the series sigma n varying from 1 through infinity 2 to the n square plus 3n over square root of 5 plus n to the power 5 converges or diverges. So let's apply limit comparison test. So you have to choose a suitable sigma bn, which you should be able to say whether it is convergent or divergent. Even if obviously it is not in the first step, but by some computation, you should be able to say the chosen series is convergent or divergent. Only then can you compare. So for this, or always we choose, you look at the given an. This is without the sigma sign. This would be our a sub n. Look at the numerator. So that is 2n square plus 3n. So choose the leading term with a higher coefficient for the numerator of Bn. Then for the denominator, again, the highest exponent, which is n to the power 5, but square root of that. So we get sigma n varying from 1 through infinity to n square over n to the power 5 halves. So it will be sigma 2 divided by n to the power 5 halves minus 2. So it will be sigma 2 divided by 5 to the power 1 half, n to the power 1 half. So this can be identified as a P series. This is a P series. If P equal to 1 half less than 1, therefore this series is divergent. In other words, sigma Bn is divergent. The chosen series is divergent. All right. Now, in order to apply the limit comparison test, we have to go with the ratio an over Bn. An is the nth term as given in the problem. So 2n square plus 3n divided by square root of 5 plus n to the power 5. And we are going to divide that by Bn. Bn, either you can take the reduced expression or you can take the one like this, which will be easier for computations. So it's 2n square over square root of n to the power 5. So you flip and multiply 2n square plus 3n divided by 2n square. Then you have this expression will go to the numerator. Square root of n to the power 5 divided by square root of 5 plus n to the power 5. That is 2n square plus 3n divided by 2n square, and square root of n to the power 5 divided by 5 plus n to the power 5. And now we are going to divide this whole thing by 2n square. This thing by 2n square, the highest exponent in the denominator, divided by 2n square. Then within the radical, for the second one, you divide by n to the power 5 within the radical. So we get 2n square over 2n square, which will be 1, plus 3n over 2n square, so 3 by 2n. That is 3n divided by 2n squared. So n gets cancelled out. So you just get 1n, the denominator. and 2n square over 2n square, which is equal to 1, and square root of n to the power 5 over n to the power 5, 1. Then you have 5 divided by n to the power 5, which becomes 0, and n to the power 5 over n to the power 5. So this is just this ratio an over bn. And now you allow n to approach infinity for this ratio. This will be limit as n approaching infinity of 1 plus 3 over 2n divided by 1 times limit as n approaching infinity of 1 divided by square root of 5 over n to the power 5 plus 1. So this part becomes 0. This part becomes 0 as well. So the limit is just 1 times 1, which is equal to 1. So this number, whenever you do the ratio limit comparison test, the limit should end up with C finite and positive. If so, then what is your conclusion? Sigma an and sigma bn behave alike. By limit comparison test, sigma an is sigma n varying from 1 through infinity. The given problem, 2n square plus 3n over 5 plus n to the power 5 within the radical. In this case, the behavior are the same. Already we stated that sigma bn is divergent. So this one is also divergent. Notice that in testing many series, we find a suitable comparison series, sigma bn, but by keeping only the highest powers in the numerator and the denominator, which is what we did even in this problem. So we kept only the highest exponent for the numerator, highest exponent in the denominator, to suitably pick the series to compare to. So in this section, you have actually covered two types of comparison test, regular comparison test and limit comparison test. The limit comparison test, it's less chance for making errors. But when you do comparison test, you can do this, the comparison test that I have done in this problem. This would work only when the numerator is a constant. If it is a polynomial involving n, then this method may not work very well. So it's limit comparison test. Even though you are allowed to choose any technique, comparison or limit comparison, then make sure that this limit comparison test is less chance for errors. And then in this exercise, suggested problems, I have done several problems in the section videos. Problem number 4 is done. Problem number 7, 8, 15, and 23. All these problems are done. Please refer to the videos for this section. Hope these videos help.